Okay, if you're watching this, you have elected the quick review of Algebra 1. We're going to go through the first 4 sections of that book that you've got. We're going to start off with real numbers and operations. Keep in mind that if you need a little more, if you find that some of these things are confusing to you, you can go ahead and look at the longer version. But it is my intent to give us a quick review through Algebra 1, and then we'll be jumping into Algebra 2. Okay. Rational numbers, what are they? Do we know what the difference is between a rational and an irrational number? Ratio is a hint here. We'll look at that in a moment. Adding and subtracting. Simple enough, isn't it? Oh, you might like to see this little cartoon here. Okay, let's see how well you understand what a rational number is. A rational number is anything that can be written as a ratio of 2 integers. There's an example of a couple rational numbers. They can be written as a ratio. So that tells us that if it's irrational, it cannot be written as a ratio of integers. How can we recognize whether or not a decimal number? You notice these dot, dot, dot at the end. That means this goes on and on like that. Some of you may have been familiar with this method of denoting that it goes on and on and on. When we have a repeating decimal like this, a pattern that goes 191919, that's the sign that we have a ratio here that can be expressed as 2 integers, and therefore this is rational. Now, how about this one? It's got some sort of a pattern going on, but is it a repeating pattern? 011, 01, no. No, it is not a repeating pattern, so this one is irrational. This will not be expressed ever as some integer divided by another integer. How about this one? Well, notice there's nothing saying it goes on any further than this, which means that it could be written. So if it's an ending, a terminating decimal, then it is a rational number. And think about it this way. I could write this as 8,714 over 1,000, couldn't I? This is a rational number. If you have a decimal that terminates, it's not being rounded, it actually terminates, it doesn't go on, then it is always a rational number. So repeating pattern, terminating, it's a rational number. Here we have something which is irrational. That is impossible to express as a ratio of 2 integers. Real numbers and operations. These are so simple, aren't they? A negative 12 plus a negative 7. 32 plus a negative 6. Decimals. We have a negative 3.4 and a positive 2.1. We're summing them together, and what do we get? How about this one? Watch out. We have different denominators. These are unlike terms. We cannot add unlike terms. We can make them alike, though, just by getting the least, we can make them like by getting the least common denominator, which in this case would be 6, wouldn't it? So we could express this as negative 10 over 6 plus 1 over 6. Now they have a common denominator. We can say negative 10 plus 1 all over 6, negative, that's an equals, negative 9 over 6, which we can simplify. There we go. Subtracting by adding an inverse. Here we're interested in something called the additive inverse, which is merely changing the sign. So if I want to convert this, subtract by adding. Sounds kind of silly, doesn't it? But we can do it. So we're going to say 7 plus. And now we're going to add the additive inverse of a positive 10. We were saying 7 minus a positive 10. Now we're going to say 7 plus a negative 10. That's the additive inverse. This one is always already expressed as an inverse. Seems, but we want to make it into an addition, so we have to say x, and now we're going to say plus instead of minus. This was minus a negative 5. What is the additive inverse of a negative 5? It's always the opposite sign. So where this was a negative 5, it becomes a positive 5. So the answer here, of course, is 13. This one I never even wrote down what the answer was, but it's a negative 3, isn't it? How about this one? We're going to convert it from a subtraction of a positive 4.1 to the addition of the additive inverse, which is a negative 4.1. We add those two together and we get negative 7.2. That's a point. All right, how about this one? Well, let's start out by converting it from a subtraction problem to an addition problem. So we've got a negative 7 over 2. We want to change it from subtracting a negative number to adding the additive inverse, which would be a positive 4 over 5. Now we still have a problem, don't we? Because we've got 7 over 2 plus 4 over 5. Whenever we're adding fractions, we have to have the same denominator. The least common denominator here is 10. So that will become a negative. To make this 10, we multiply the top and the bottom by 5, negative 35. To make this into a 10 in the denominator, we multiply the top and the bottom by 2. That's all over 10. We end up with a negative 27 over 10 as our answer. And I don't think we can get that any smaller. We're going on to section 2 now. Multiplication and division of real numbers. Multiplying, dividing, knowing that, and we do know this, don't we? We cannot divide by 0. Let's just pause for a moment to look at this little cartoon. Okay. Multiplying. A negative times a positive will always be negative, won't it? So this would be negative 99. A negative times a negative, if we've got two negatives, an even number of negatives, it will always turn out positive. So this would be a positive 28. Here we have three negatives. That's an odd number of negatives. It's going to give us a negative result. 1 times 1 times 1. Division. And here we're going to divide by multiplying. Divide by multiplying. Okay, let's write it out as a more obvious division problem. Negative 24 divided by 3. Isn't that what this says? Okay. So remember what we did back in elementary school? Stay, change, flip. We stay the same. The change we're talking about is moving from division to multiplication. So multiply by, and we flip means we consider that as a rational number and we take its reciprocal, 1 over 3. So divide by multiplying by an inverse. Here we're talking about a multiplicative. You need to know these terms. And I better spell it right for you too. Multiplicative inverse. Okay, so that will turn out to be a negative 8. Right, we had one negative, so it stays negative. The only time a negative becomes positive is when we have an even number of them, which is the case here. So this is going to become positive. I'm going to write it as 15 divided by 3. So I noticed that I had a negative here and a negative here, so I could write them both as positive. Then I'm going to do stay, change, and flip, which becomes 5. How about this one? Stay, change, flip. Multiplicative inverse is this reciprocal. Now, fractions are so much easier when you're multiplying. We don't have to worry about least common denominator. That's only when we're adding. For multiplication, how simple is this? We just multiply the numerators, place that over the product of the denominators, and we are done. How sweet is that? Let's try this one. Stay, change our symbol to multiplication, and flip. So we're going to have a negative 11 over 6. Negative 44 over 30. But we wouldn't leave it like that, would we? Because we notice these are both even numbers, which means we can at least factor out a 2. So if we divide the top and the bottom by 2, we get negative 22 over 15. Which of the following divisions are possible? Now I want you to remember something here. This is the order of operations, PEMDAS. We've got a denominator, which is a little bit complicated looking. So recognize that this is isolated from the 6 and it could be considered as being in parentheses. We need to do what's in the parentheses first. And when we start looking at what's within the parentheses, we notice we've got subtraction and we've got multiplication. Which do we do first? Multiplication. Subtraction we do much later. So we get 6 minus 6. Now we do our subtraction, and we get 6 over 0. This is not allowed, is it? Copy that. I think I'll make it smaller so it fits a little better. And I'll make another one just in case we need it. So, no, we don't like that. Not allowed. Never divide by 0. How about this next one? Again, now we have in the numerator a fairly complex expression, and we should deal with that as if it were in parentheses. We need to take care of any exponents, right, before we do anything else. So 4 minus 4 over 8 is 0 over 8, which is perfectly acceptable and will be 0. Now this one, when you first look at it, I know what you're thinking. Same thing I was thinking. Okay, numerator, denominator, identical. When that happens, it's equal to 1. Almost always. This is the exception. And why is it the exception? Look at what your denominator is equal to. 0 over 0. Now, can't be done. Whoops. Sorry. Can't be done. No. Okay? So no dividing by 0. We're now in section 3, algebraic expressions, writing equivalent expressions. We're going to talk a little bit about properties of numbers to help us do this. Evaluate this. So we've got 3, and instead of x, we're going to use 4 minus 7. So that's equal to 5. How about this one here? Instead of using x, now watch this because I have to isolate. See how we have a negative here? I have to account for that. And what am I putting in for my x? A negative 3. You can see why that was important. It makes a pretty big difference. If I had not done that, I might have confused myself on these negatives. I actually have 3 negatives here, so we're going to have a negative result. 1 times 3. That's my answer. How about this one? Here we've got an x minus 7, which is in absolute value. We're trying to evaluate this for x equals 5. So we will have the absolute value of negative 2, which we know is 2. We always strip away the negative when we deal with absolute value. Here are the properties that you need to know. We're going to spend a little bit of time doing some examples. Commutative. The part you can pay attention to here is commute. So if x commutes from the first position to the second, and y commutes from the second position to the first, that's commutative property, which is perfectly acceptable in addition. You can also do that in multiplication. The associative property, you'll notice there is nothing different. X plus y plus z. X plus y plus z. Their positions are the same. It's not commutative. The only difference is how things are grouped. So in addition, you can regroup them like this. It doesn't change their value. You can do the same thing in multiplication. It does not change their value. So that's the associative property. The identity property, people do get confused on this. What's the identity property of addition? 0. What do we mean here? If I add 0 to anything, it doesn't change its identity. But when we're talking about multiplication, the identity property there is 1. You know that too, because if we multiply anything by 1, it still retains its identity. We've been talking about inverses already. If we're talking about the additive inverse, we're talking about the opposite sign. If we're talking about the multiplicative inverse, we're talking about flipping, right, the ratio. Keep these all in mind. We're going to use them right now. Well, apparently not immediately. Rewrite this as an addition. So instead of subtracting a positive 4, we are going to add the additive inverse, which is a negative 4. Rewrite this as a subtraction. This is a rather unusual thing to do, but we'll go ahead and do it. It's just a matter of practicing this. So instead of saying x plus a positive 3, we're going to say x minus, and then we're going to do its additive inverse, which would be a negative 3. Those are equivalent. Use the commutative. Now this is about location within the expression. Use the commutative property of addition. Okay, so the first shall become the last, and the last shall become the first. Now we're going to use the commutative property of multiplication. We're looking at this factor, which has 2 terms in it, and this factor. Our first factor becomes our second, and our second factor becomes our first. Commutative property. Now we're going to do the associative property of addition. It's going to have everything in exactly the same position. What's going to change is just the association. This one groups the second and third. We're going to group the first and second. How about the associative property of multiplication? Same principle. We're going to keep everything in exactly the same order. We're not going to use the commutative property. We're going to use the associative property. It associated the 8 and the x to the third. So we're going to change that to associate the x to the third with y squared. And keeping on with this. Ooh, this is a tricky one. Commutative and associative properties. Let's have you do this one on your own. I will look in your notes to see this one. Okay? Notes. So write it down right now. You don't have to do it right now. Write it down right now and make sure you do it before you come into class. Or you can pause this and do it. Write an expression equivalent to this using, what is this? This is an identity factor for what? For multiplication. So an expression equivalent to this would be 3/5 times 1, right? And this is just a fancy one, 7 over 7, which we all know is equal to 1. And we have 21 over 35. Write an expression for this by simplifying. Well, I notice right off we have something which is equivalent to 1 in there. So I can say 3b over 6c. And the 3 over 6 simplifies. There we have it. Show that this is equivalent to this. Well, the only difference I see are these two middle terms. And what do we know about these? These equal 0. And what do we know about adding 0 to anything? That's the additive identity. It doesn't change its value. We're going to end with this section, the distributive property. We use it to multiply, and we actually use it sort of in reverse to factor. Collect like terms by applying the distributive property and then simplifying. Writing the inverse of a sum, simplifying expressions. All of those use the distributive property. So we're going to start with this one. 5y plus 15. Remember, whatever you have here distributes to every term within your parentheses. This becomes RA plus RB plus RC. This becomes, watch this, because we've got a -1 times A. I could do them separately. If I did them separately, suppose I just distributed the -1 for my first round. I'd have A, -Z, -2. And then I could go for my second pass, which would give me -AZ, -2A. How about this one? Let's just do this all at once here. This will be a -5, notice this, x squared, x times x, and a negative times a negative. Okay, multiplying. Now factoring. Factoring, we are going to look for something common that we can pull out of this. How about the factor of 9? If I divide this by 9, I have x, and I divide this by 9, I have y. To check my work, we can always do this and make sure I get back where I started. How about this one? What's common that I can factor out here? How about a 3? And this one, I have an A. Now this one's tricky because a lot of people will confuse these identity relationships. If I am dividing A by A, what am I going to have? 1. And dividing this by A, you won't be confused by that one. Now if you're ever uncertain, just go back and try it and make sure when you distribute it back you get what you started with. Collect like terms. How do we know they're like? They have exactly the same variables with exactly the same exponents. What's the exponent on this one? Nothing is written there, but the exponent is actually 1. When the exponent is 1, we don't bother writing it. We just write it when it's something other than 1. So this would be 11x. Those are all like terms. They can be added. A and A, I have these two that match. And B, B. Those two match. Same variable with the same exponents, 1 and 1. Same variable, same exponent. So let's combine these two. I get right? We are cruising. Now we're going to use the distributive property to simplify. If I distribute the negative into here, what do I get? Positive 1. If I distribute it into here, I get a negative z and a positive 7. If I distribute it in here, I get a positive 3a, a negative 2b, a positive c. And this one, it's fairly simple, is it? It's just getting longer. We started with 1, then 2, 3, and now here we have 4 terms. We always distribute to all the terms within the parentheses. Negative 9a, positive 4b, whoops, what happened to that? A positive c, and a negative d. We are simplifying these expressions by distributing the negative. This one looks a little complicated, but it really isn't. We just have to recognize we've got 3 terms. Here's one of them. Here's another one. And here's another one. So the terms aren't going to change. What is going to change? Just the sign. So we end up with a positive 1/2, a negative 2/3 x, a positive 4/7 times x squared. Simplifying with the distributive property. How about this one? We're going to simplify. Okay, we're going to start by distributing that negative. So we'll have 4a minus a minus 5. Both the a and the 5 were positive, so when I distribute the negative, they both become negative. That will simplify now. I've got 2 like terms right here. I can combine them and it'll give me a 3a minus 5. This one, I need to distribute this negative. 2z minus 4w, that's minus. Nothing changing there, but these two are changing. I had a positive 5z and a negative 3w. When I distribute this negative, it all changes. So these w's, I can combine them, can't I? And the z's, those can combine there. In both cases, the same variable at the same with the same exponent. That turns out to be a negative 3z and a negative w when I finish that. Here I'm going to be distributing a negative 4. So I get 3z, negative 4z, negative 8. After I've done that, I see that I've got 2 like terms. I can combine those, a negative z, negative 8. All right. Oh! These are getting more complicated. We start from the inside out. Remember that? You always deal with the innermost parentheses first. So this equals 9. And I'm not going to do anything with this bracket yet. I'm just going to deal with what's inside the parentheses. So I'll have negative, these are both positive, they're going to both become negative. So negative 3x, negative 3. Now I'm going to deal with the brackets. I'm going to be distributing this negative 2. So I've got a 9, negative 4, positive 6x, positive 6. Oh, okay, I can combine this and this and this. Right, those are all like terms. They're simply numbers. We know we can add numbers. So I've got, what does that turn out to be? 11 plus 6x. Same thing again here, only even more nested. But I follow the same rules. I'm going to, oh, maybe I'll go down here. 4 plus a times what's in the curly bracket. I'm going to leave what's in the curly bracket alone. It's going to be 3 plus b, and then we've got the square bracket, and I'm going to leave what's in the square bracket alone. The only thing I'm actually going to change is going to be right here. So it's going to be a plus 2d plus 2. I don't have any like terms to combine there. Now I'm going to deal with the square bracket. Notice how I'm working from the innermost out. Think of it as nested, and you always go to the innermost. I'm not going to deal with the curly bracket right now. That's going to stay right there. I'm just going to deal with the square bracket. So my 3 is untouched, plus BC plus 2BD plus 2B. Now, let's take care of the curly brackets. This is a very unsatisfying example because we don't get any simplification at all. So we're going to end up with 4 plus 3a plus, I kind of like this one, ABC. You should put them in alphabetical order like that. Plus 2ABD plus 2AB. Oh my. Okay, how does that look to you? We have one more to go, I think. Oh, there's really nothing to do here. This is just looking at what we've added. We had already looked at commutative, associative, identity, and inverses, and we've just added in the distributive property and how that works. So there was the quick one in 38 minutes. If you have questions, go to the extended ones. They take a lot more time, but they give you a lot more background. Don't bother doing it unless you really need it. But if you need it, it's there for you.